Hello, my name is Nathan Farmer, and welcome to my presentation on our fifth lab, Breaking with Faraday's Law. So just as the name of this lab suggests, the purpose of this lab was to observe how a magnet falling through a conductive tube can generate this breaking magnetic force on that magnet. Once we observed that, we wanted to model those observations computationally and compare them to one another. So throughout all of this, we needed to keep a few physics principles in mind. For example, the strength of magnetic forces and what changes them, the magnetic forces on magnetic dipoles, how they interact, and magnetic flux, and how this change in magnetic flux can induce a current and induce a magnetic field as a result. So the experimentation portion of this lab was very quick actually, and it just took place, and I dropped a magnet through some aluminum foil with these dimensions here 5 times and recorded it. And once I had that recording, I went through and I scrubbed through the video to analyze the exact time it took for that magnet to fall that distance through the tube. As you can see here, that time was 0.699 seconds, which is nearly 3 times greater than the theoretical time it should take without any aluminum foil. So once I had that average time that it should take, I wanted to compare this to the physics principles that we've learned and see how it compares. So to do this, I create a computational model of that experimental setup. The first thing I have to do here, though, is I need to input my real-life conditions. So the length of the tube, the width, the inner radius, all of that, and assign them to variables so that I can use them later. And then I need to create these functions to calculate B field and the change in flux over time. These are both very important for calculating the force that's going to be induced later. So that's why we do that. And then additionally, actually how we create this setup is we start off by just creating a tube by making a bunch of different rings and stacking them on top of each other. And then we want to integrate over each of these rings to calculate the change in flux from that falling magnet. And as a result of that, what induced current is there going to be and what magnetic field is going to be generated as well. And once we know that magnetic field, we can calculate the magnetic force that's going to be acting on that magnet. So once we have the magnetic force from that particular ring, we can do the same thing over and over again and summate all of these forces and then obviously add gravitational force to get the net force on that magnet. And once we have net force, obviously using Newton's second law, we can calculate the velocity and the position of that bar magnet. So once we've done that, we can this is what our final model looks like. This is after the magnet has already fallen all the way through it, and the velocity versus time graph, as you can see here, shows how it starts off accelerating downwards, and then once that magnetic force equals that of the gravitational force, the velocity stays still until it falls out of the tube. So as you can see here, the computational time was 0.867 seconds, whereas my experimental time, as you remember, was 0.699 seconds. And you can see that these are fairly similar values, but there may have been a few things that could have caused the discrepancy here. For example, the width of my aluminum foil may have been a little bit too small, since the experiment asked to use at least 1 centimeter, and I only had half a centimeter of foil surrounding my tube. And then additionally, sometimes calculating the time that it took the magnet to fall was tricky, since I didn't have enough high enough video frame rate to find the exact time that it fell out of the tube. Additionally, just a few follow-up questions. What if the resistivity of the conductor were reduced to as close as possible to 0? Well, obviously, since we know that the current is just going to be that EMF over the resistance, the smaller that gets, the greater that induced current is going to be. And when the current increases, that magnetic field that it produces to slow down the magnet is going to increase as well. So additionally, what if we cut holes or slots in the tube? How would this affect the rings current in your model? Um, Obviously, this would reduce the induced current, and as a result, cause the magnetic field generated by Faraday's law to not slow down the magnet quite as much. Thank you so much for watching my presentation.